So today we're going to be working through problem 4.4 from chapter 4 of Taylor's Classical Mechanics. This problem says we have a particle of mass m moving on a frictionless horizontal table. It's attached to a massless spring whose other end passes through a hole in the table. So we have something like this. We have a hole in our table. We have a string with a mass on the end traveling around. The string is going through and it's being pulled downward. So initially we have a circle with a radius r naught and an angular velocity omega naught. Now we're pulling the string downward, and that will be important for part 2, this pulling it slowly so that we can approximate it by a circle of slowly shrinking radius. This is so that our force is just mass times the acceleration of that pull, and not any additional acceleration happening to that mass that we have to account for. So it's asking us, what is the particle's angular velocity once a length r remains between the hole and a particle? So we're going from r naught to r, and we're going from omega naught to omega. And this is the conservation of angular momentum, that L naught is going to equal the final angular momentum. And our initial is going to be mr squared omega naught is equal to mr squared omega. Those m's will go away. We're going to be left with r naught squared over r squared. Omega naught equals omega. Carry this down. We have omega equals r naught over r squared omega naught. That covers part A of our problem. So now for part B. This is where that acceleration becomes important. Assuming that the string is pulled slowly, you can approximate the particle's path by a circle of slowly shrinking radius. How much work is done in pulling the string? So we know that we're going from r naught to r. We're going from omega naught to omega. And we want to know the work done in pulling the string. So you have centripetal acceleration is v squared over r. Omega is v over r. And that means that v is omega r. So this centripetal acceleration in terms of angular velocity becomes omega squared r squared over r, which is omega squared r. So we know that force is mass times acceleration. So our force from that centripetal force is going to be m omega squared r, which we know what omega is equal to up here. It's going to be m r naught over r squared omega naught squared times r. So our centripetal force is going to equal mass times r naught to the fourth over r to the fourth omega naught squared. One of those r's is going to divide out, so we're going to be left with m r naught to the fourth over r to the third omega naught squared. Now, our change in radius is going to be a small value dr. We know that our work is force times distance, and if we integrate that from our initial radius of r naught to our final radius of r, we'll be able to find the work done in moving the mass and shrinking the radius of that circle. We know we're shrinking the radius, so we're going to place a negative on the dr. So that's our distance. Now, we can set up an integral from r naught to r of m r naught to the fourth r prime. This is just to prevent any confusion amongst this r up here. R prime cubed omega naught squared negative d r prime. Evaluate from r naught to r of, we'll go ahead and pull that out front of the integral right now, m r naught to the fourth omega naught squared times the integral from r naught to r. We can go ahead and switch our limits of integration to get rid of that negative. So we'll go from r to r naught of 1 over r prime cubed dr prime. And that's going to be m r naught to the fourth omega naught squared. Integral from r to r naught of r prime to the negative 3 dr prime. It's going to be m r naught to the fourth omega naught squared. It's negative 1/2. And it's going to be 1 over r prime squared. And then we're going to evaluate this from r to r naught. Once again, we can get rid of that negative, switch our limits of integration. And that'll be 1 over r squared minus 1 over r naught squared. This is our work. That answers part B of our problem. Now, what is part C asking us? Part C is asking us to compare the answer from part B, where we calculated the work, with the particle's gain in kinetic energy. So, we know that our change in kinetic energy is going to be 1/2 mv final squared minus 1/2 mv initial squared. So it's going to be 1/2 m vf squared minus v naught squared. And we know that v is omega r. So our from here, this expression we're going to use v is omega r, and we are going to calculate our initial and final kinetic energy to calculate the change in kinetic energy. So for our final velocity, we're going to use v is omega r, the final omega, and for our initial, we're going to use omega naught. So we will have omega squared r squared minus omega naught squared r naught squared in our parentheses there times 1/2 m. And we know that omega was r naught over r. Our final was r naught over r squared omega naught. We're going to square that times r squared minus omega naught squared r naught squared. And we're going to have 1/2 m. That's going to be r naught to the fourth over r to the fourth omega naught squared times r squared minus omega naught squared r naught squared. See here, we're going to have 1/2 m. That's going to work out to be r naught to the fourth over r squared omega naught squared minus omega naught squared r naught squared. And you can see that if we pull out an r naught to the fourth, 1/2 m r naught to the fourth, and an omega naught squared, we factor that out, we're left with 1 over r squared minus 1 over r naught squared. You can see that the change in kinetic energy is equal to our work. We end up with exactly the same expression, so our change in kinetic energy is equal to the work done.